So I'll hopefully be able to at least give you a brief understanding of the immersed boundary method. As we would imagine, like solid-fluid interactions have immense industrial as well as research importance, ranging from everything from atmospheric dust suspensions to industrial scale fluidized bed reactors to slurries in subsea pipelines. And coming up with models to capture that behavior is quite challenging because we're trying to marry two quite unrelated pieces of mathematics. For the stuff I'm going to be interested in, we'll be looking at rigid body motion described by Newton's equations, as well as the incompressible fluid flow described by Navier-Stokes. Coming up with a way to marry these two equations can be difficult because you're dealing with typically a Eulerian frame for the fluid, and a Lagrangian frame for the solids typically. So there's roughly 3 techniques that are used. One is conformal mesh, in which you solve the solid and fluids sort of monolithically, and the fluid mesh is based on the shape of the solid. But that limits the kind of solids you can model because it has to be a fairly simple hull. Or you can have a deformable a deformable mesh which moves with the solid. However, that becomes very computationally expensive because you have to regenerate these random meshes every time step, which just can blow up your runtime. In order to sort of solve the problems of these two problems, in the 1970s, the immersed boundary method was first proposed, in which you separate the solid and the liquid solvers to a large degree. This then allows you to have both complex geometries as well as flexible, deformable solids, which I won't cover. But for example, Tim's group uses it for blood cells, in which the deformation is going to be quite large. So, that's not. I was just looking at, just shows you the same object in both frames, in the frame of the fluid and the frame of the solid. So the way the immersed boundary method works is you can typically have any kind of mesh for the fluid. What tends to be used is either a Cartesian or an adaptive Cartesian mesh. And then you have a representation of the solid that is immersed on that mesh, or sort of placed on the mesh. And at every point where the boundary of the solid intersects with a fluid mesh element, we place a point, sort of a Lagrangian point on the surface of the solid. And then we use several different kinds of interpolation techniques that you can use then to go from the solid mesh to the fluid mesh. So probably ones that are typically used are sort of a weighted quadratic distance model to sort of interpolate between the two meshes. So basically what happens then is you have this two-way communication at any given time step between the fluid and the solid. And then that just gets separated directly to every time step. So I look at it, I also use Garris because why you write software, like if you can get it off the internet, as well as so we've implemented an implicit immersed boundary method where the coupling is done using a volume of fluid approach on the edge of the solid, which is then our interpolation method. So that then allows us to capture the force on acting on the solid by basically integrating across the stress and strain tensors on the solid surface, as well as then we couple back to the fluid by setting all of the mesh elements which contain at least some part of the solid, using a volume of fluid approach to then apply the zero slip condition along the edge. The solids are, at least in GIS, are then handled by another piece of open source software called the Open Dynamics framework, which handles all the complexities of 60 days of motion solver. That's basically what happened. So I'll walk you through a typical time step in our solver. Is gas solves fluid. We then, from that, calculate the hydrodynamic forces acting on the solid. We have the majority of the time step is actually involved in calculating whether any two solids will interact or collide, because this immersed boundary methods don't work very well if you have two separate solids actually coming close enough to each other to collide. So we have a force field as well as a constraint-based contact model to make sure they stay away from each other to avoid any numerical problems. And at the next point, then we iterate our solid domain and we regenerate our Cartesian mesh to ensure that we maintain our mesh adaptation criteria. So that's basically the same, except we integrate the hydrodynamic forces across the surface elements, and then we set the fluid's velocity proportional to how much of any given fluid mesh cell contains. A bit of a speed up. We can actually neglect or drop out all this fluid nodes which are completely inside the solid, and that has a marginal speed up in the solid time. So this is all well and good, but it has to match reality at some point. So we've looked at cases where viscosity is a major factor. For example, settling of spheres, as well as the lift generated by a tumbling oblate spheroid next to a wall, and we can see very good agreement between our models and analytical results. Then we decided to take it a step further to push beyond sort of well-known well-known examples to see how far we can take this sort of approach. We settled on looking at the motion of an triaxial ellipsoid in either an inviscid case or in a very high Reynolds number fluid. The reason we've done this was in the 80s it was shown that for any solid which doesn't have a plane of symmetry, the motion should become chaotic, because you can show this by taking a reduced order model. You can show under these conditions that the equations become non-integrable. So our key parameters for this particular model is the energy ratio, which is basically how much the particle we're considering translates versus rotates and at an initial perturbation. And then in order to actually get data out, we put a marker on the longest edge of the ellipsoid we're studying. So basically what happens is, as you increase the energy in the system, it transitions from a sort of a periodic-ish behavior where where it just sort of tumbles along to a very chaotic behavior as you increase the energy ratio. And this was predicted using analytical approaches. This was predicted by Erich and Jones using a reduced order model, and we can see we have very good results using our immersed boundary method as well compared to the numeric results, which sort of gives us great confidence that the method works, especially for cases where you would expect sort of these DNS type solutions to start breaking down. We've also then pushed further in looking at going beyond the assumptions of Erich and Jones of a purely triaxial ellipsoid, having a symmetric ellipsoid but having viscosity play a role, and you can see these sort of very nice weight sheddings, which then breaks the symmetry of the system and allows us to have chaotic dynamics return, and it's quite exciting. Sorry, coming back to immersed boundary methods, I would definitely recommend the first paper by Duna on the immersed boundary methods. It walks you through the basics as well as a lot of the completion details. So, any questions?
Thank you very much. We have plenty of time for questions.
Have you tried to extend this to multi-fluid systems? So let's say when you have a particle moving about and it's close to a surface,
Between like having two fluids. I haven't looked at that yet. Been looking at having viscosity gradients in the fluid, but I haven't looked at having two fluid phases. It should be you should be able to do it.
yeah, the one thing might seem like a first non-trivial.
Yeah, like
you may be able to operate in time regimes.
you might have a good point. Like the wetting would probably be the major problem with that.
For this solid ellipsoid, are you forcing only outside the body, or are you also forcing inside?
For the initial conditions?
No, for the IBM coupling.
So we force on the outside, not on the inside.
Would this method work for multiple solid objects hitting each other?
Yes, so if I go back, actually most of our solvers' time, any given time step, is spent working out whether two or more solids will collide, and then whether we have a contact model to sort of approximate elastic conditions in that situation. I didn't include the results we have on that. Thanks for sharing.
Yeah, your previous slides, I saw mentioned fluidized bed reactors. Is this applicable for FCC cyclones?
So at the moment, this particular solver, we can handle a small number of solids in any given fluid domain. In theory, if we could speed up or optimize the current, maybe, but at the moment, I wouldn't venture that you'd be able to use it in a cyclone.
I've seen a few more fingers.
In immersed boundary method, do you need to maintain all the time the shape of the particle? I mean, that was supposed to be a spherical particle. So, do you all the time during the running computation, all the time you are maintaining the shape of the particle? I mean, it remains all the time.
So the method doesn't require the shape to be held constant. The method does allow for flexibility. In ours, we assume we maintain the shape to be rigid, but the method in of itself doesn't require that.
Thank you.
Yeah, is it going to be applicable when you have dense particle concentration and you have to consider the particle-particle interaction, something like that?
So looking at dense particle suspension, the particle-particle interaction would be significant. It's part of our contact model. Again, you run into the problems of just how computationally expensive it would be to have really dense suspensions.